structure of the atom. So, the question is, why do we care? Why are we bothering to look at these subatomic particles? Why do we care what the atom actually looks like? Well, those parts, those subatomic particles, actually determine the properties of the atom. So we've looked at physical and chemical properties already in this course, and so now we're going to look at how do those subatomic particles actually affect the properties. So those three parts again: electrons, protons, and neutrons. All right. So, quick summary: protons, they're found in the nucleus. They have a mass of 1. Now, this is a new unit of measurement for you. So you're all probably pretty familiar with kilograms or pounds to measure the mass of something. Protons are really small, and we are not going to try to add up the mass of the protons in an atom using kilograms. It's just not going to work. So what scientists did was they created a new system of measurement. They just said, all right, fine, let's make life easier on ourselves, and we're going to say the mass of a proton is 1, and we'll just compare everything to protons. And so if you have 5 protons, you have a mass of 5, and that AMU stands for atomic mass units. All right? So the charge on a proton is positive, the mass is 1. Neutrons, also found in the nucleus, conveniently have the same mass as a proton, so we also say they have a mass of 1 atomic mass unit. And neutrons, neutral, have no charge. Electrons are found in orbit, or in orbitals, or in electron shells. Their mass is so small that we basically consider it 0 compared to the proton and the neutron. They have a negative charge. Now, if you were to take around 1,800 electrons, you would have the mass of about 1 proton. So that's why we don't really care about the mass of an electron, because we just need so many electrons to equal the mass of a proton that they're basically nothing. It'd be like weighing yourself and then cutting off your hair and weighing it again. It really wouldn't make a difference. You wouldn't even notice it. All right. So, looking at the structure of an atom, each element has a different number of protons, neutrons, and electrons. And because of that, they have different physical and chemical properties. So the physical and chemical properties we've already talked about in class come from the number of protons, neutrons, and electrons in an atom. Now, we have 2 numbers that we're going to need to know. One is what's called the atomic number, and the atomic number tells you how many protons an atom has. So the atomic number is equal to the number of protons. It is also equal to the number of electrons. So if you know the atomic number for an atom, you already know how many protons and how many electrons it has. The atomic mass, or mass number, is equal to the number of protons plus the number of neutrons. In other words, the heavy parts of the atom are what we add up to get the atomic mass. So all of the heavy particles in the nucleus add up to make our atomic mass. And remember back to the solar system model, right? We've got this heavy nucleus in the middle, just like we have a heavy sun in the middle of our solar system. All right. Now, the next question is, where do you find those numbers? Where do you get the atomic number? Where do you find the atomic mass? Well, the periodic table. And if we look at the periodic table, depending on which periodic table you look at, you will see a couple of different numbers that are included on it. Now, periodic table is a table of the elements, hence called the periodic table of the elements. So every atom we can think of as a single particle of an element, hence the periodic table of the elements. So if we have a single hydrogen atom, we have a single atom of that particular element. Now, if you look at any periodic table, it will have a legend on it. And we're going to spend some more time later this week looking at the periodic table in a little bit more detail, but for now, what we're going to do is just look at what kind of information we can find right here. So if we look at the legend, it will tell you what each part of that means. So up in the top left corner, we have the atomic number, and then we have the element symbol, and then we have the element name, and then we have the atomic mass. Now, here is a very, very important piece of information. Every periodic table looks different. The numbers move. All right, so this particular periodic table has the atomic number up in the top left corner, and it has the atomic mass here. But not every periodic table looks the same. So look carefully. All right, so look carefully at this one and compare it to this one. So this is a different periodic table. Now you'll notice that instead of in the top left corner, we now have the atomic number in the top middle, and there's no mass at all. And then compare it to this one. Now it's a little harder to see on this one, but here's our symbol here up at the top. Again, we've got the atomic number, and we've got the atomic mass at the bottom. What about this one? Well, in this one, the atomic number is now in the top right, and the atomic mass is now in the top left. All right, so you have to be very careful when you're looking at a periodic table that you always have to check the legend to make sure you know what number is what, because they will move around depending on who made that periodic table. So going back to the first one that we had, if we also look at the element symbol, so right in the middle, we've got the symbol for, in this case, hydrogen. Now, if the symbol is only one letter, it's capitalized. So you can see that here, hydrogen. Look over here, boron, C, N, O, all right? However, if the symbol has two letters, so for example, Li, Be, Mg, you'll notice that the first letter is capitalized and the second letter is lowercase. That is important. You cannot write this incorrectly because, for example, if you were to write copper with capital C, capital U, it wouldn't be copper. It would be carbon and uranium. All right, so it's really, really important that when you're writing down the symbol for an element, that the first letter is capitalized, and if there's a second letter, it has to be lowercase. If it's not lowercase, it's not right. All right? Now, next thing, something called standard atomic notation. If we were to look, let's go back here, if we were to look at our periodic table, again, remember, these numbers can be in different places depending on what the periodic table looks like. So what we can do is take that information and set up what's called standard atomic notation. This is not the periodic table. This is just information we have taken from a periodic table. And there are three things here. Number one is the atomic mass. We put it up in the top left. Number two is the symbol. We put it here. And number three is the atomic number. We put it in the bottom left. The atomic mass is always going to be the bigger of the two numbers. Right? The bigger number is always going to be on top. And there's a reason for that. I'll show you in a second. Why would we do this? Well, those two numbers are going to help us figure out how many subatomic particles can be found in an atom. So, a reminder. The atomic number tells us the number of protons, and that we usually use the symbol P for. The atomic number also tells us the number of electrons, and we use the symbol E for that. But what about neutrons? How do we figure that out? Well, remember, the atomic mass is the number of protons and the number of neutrons all added up. That's where all of the mass of an atom comes from, because the electrons weigh so little that we don't care. So, P, the number of protons, plus N, the number of neutrons, gives us the atomic mass. So how do we use that to figure out the number of neutrons? Well, P is the atomic number. So, the atomic mass minus the number of protons equals the number of neutrons. So the atomic mass minus P will give us N. So why were we talking about standard atomic notation? Well, watch. At the bottom, we have the atomic number, which is equal to the number of protons and the number of electrons. So right here, we have neon. And because the atomic number is 10, that tells us it has 10 protons and 10 electrons. The atomic mass minus P gives us N, which we just talked about in the last slide. So 20 minus 10, so the atomic mass minus P, or the atomic number, equals 10. So that means that neon has 10 neutrons, because it's the mass minus the number of protons. 20 minus 10 gives us 10. So the whole point to this, the whole point of standard atomic notation, is that by setting this up, we can figure out how many protons, electrons, and neutrons every atom has. The atomic number is the number of protons and the number of electrons, and then we take the mass minus the atomic number to give us the number of neutrons. All right? So I want you to practice. I want you to try this. I have two elements here. I've got an atom of nitrogen and an atom of bromine. Now, you could get information from the periodic table. I can give you information. It depends on what the scenario is, but in this case, I'm going to just tell you. You have an atom of nitrogen with 7 protons and 8 neutrons. What would the standard atomic notation look like? So I want you to pause right now, grab a piece of paper, and try to figure out what standard atomic notation would look like. I'll give you a second to pause it. All right, so now that you're back, 7 protons, so a 7 goes here, and we have 7 protons and 8 neutrons, so 7p plus 8n means we have an atomic mass of 15, so the 15 would go there. All right, so let's try it again. We've got an atom of bromine. It has 35 protons and 36 neutrons. What does the standard atomic notation look like? Give you a second to pause. All right, so now that you're back, 35 protons means we put a 35 in the bottom left, and then 35 plus 36 gives us an atomic mass of 71.